So the message that I want to give you today is that the laser cooling of molecules is really coming of age. And in my group, we've been working on these two molecules, calcium fluoride and ytterbium fluoride. But really, there are many molecules that you can work with now. Let me first of all tell you some reasons why you might like to have ultracold molecules. I think they're all well known. First of all, if you have an array like this of polar molecules able to interact with each other through their electric dipole moments, then you have the possibility to build a quantum simulator of quantum many-body systems. And one thing that's nice about this is that the interactions are controllable because the dipole moment of a polar molecule is zero unless you have some field to induce a dipole moment. So that's one application. Another more technological application would be to think about building some kind of quantum processing circuitry. And there, the molecules may play a very useful role in storing quantum information in their rotational states. Then there's the question of ultracold chemistry. I was astonished to learn some years ago that even the best quantum chemists in the world have difficulty telling me what will happen if I collide a single atom with a diatomic molecule. So the idea is that these atoms may interact in some way, and then we don't really have a good way to calculate what comes out. Now, this is mainly controlled by the very, very tiny energy changes at the entrance and exit channels, and maybe it's not so interesting for chemists. But I think there's another aspect of this, which is that you might hope to be able to synthesize, to build molecules one atom at a time once you understand how to control all this. So I think it's a fascinating topic. And finally, something very close to my own heart is if you have ultracold molecules, you can do very precise measurements of the molecule. And here I show you a Feynman diagram which is intended to indicate how the electron may acquire an electric dipole moment by the emission and absorption of a virtual particle here, which has the property that it violates CP symmetry. Such an interaction is believed to exist, but nobody has ever seen it. And those of us who measure the permanent electric dipole moment of the electron have been pushing the limit down and down and down, and theorists keep on saying, well, okay, just go a little bit further. So with ultracold molecules, you can go actually a lot further. So I think that's very exciting. So there's been an explosion of progress in laser cooling molecules. Here are the species that have been laser cooled. Strontium fluoride in Dave DeMille's group initially. This fluoromethane, yttrium oxide, calcium fluoride, strontium monohydroxide, and ytterbium fluoride. That last one is the one that we like for measuring the electric dipole moment of the electron. So a lot has happened, and more than that, some of these can be magneto-optically trapped now. And you know how important magneto-optical trapping was for cold atom physics. Now it's becoming important for cold molecule physics. So these species here, strontium fluoride, calcium fluoride, and yttrium oxide, have all been magneto-optically trapped in the last few years. The kind of temperature that one gets is quite high, surprisingly high, compared with what you would get, say, for a rubidium or a cesium mott. And I'll come back to why that is the case. But typically, it's about 1 millikelvin. But now we know how to produce sub-Doppler cooling. So we can get well below 1 millikelvin, and that has been done in calcium fluoride and strontium fluoride. And the record in my lab, anyway, is 7 micro-K. I think that's about probably as cold as any laser-cooled molecules have been made so far. Once you have a cloud of laser-cooled molecules at a few micro-K, it becomes straightforward to trap them in a conservative trap. So magnetic trapping has worked for these two molecules, and the optical dipole trap has worked for calcium fluoride in John Doerr's group just recently. Now you have them in the conservative trap. What are you going to do? Well, you do some quantum manipulations, some ultra-precise metrology or measuring some some quantity or doing some information processing, whatever you like. It's time to do coherent manipulations, and now we're beginning to do that. So my talk is, well, somewhat parochial. I want to tell you about the calcium fluoride, mostly about the calcium fluoride experiments that we've done at Imperial College, but I wanted you to be aware that there's a wider activity in many groups now, and that this subject looks as though it has a long and bright future. So here is the experiment at the Center for Cold Matter in London to slow and trap calcium fluoride molecules. We have a source of molecules here. It's a beam, and in the beam there are these calcium fluoride. Now, the first thing we want to do is to slow the molecules down. Let me tell you about the beam just briefly. The beam is pulses, so we have pulses of molecules which are about 1/4 of a millisecond wide, and the speed of this beam is about 150 meters per second. That is faster than the capture velocity of a mott. So before we can capture it, we have to slow it down, and we have some slowing light here, which just uses resonant scattering to decelerate the beam. Once it's slow enough, well, then we make a mott here, and I just want to tell you a little bit about these various steps. So first of all, we use a cryogenic buffer gas source of calcium fluoride. This is the type of approach that was pioneered in John Doyle's group in Harvard. Our own particular design here is this mixing chamber into which we flow some 4 Kelvin helium gas. A laser comes through this window and hits a calcium target. So a hot plume of stuff comes out, including calcium. And then coming down this tube, we have sulfur hexafluoride, which contains, well, fluorine. So all of this mixes and cools, and by the miracle of chemistry, out comes calcium fluoride here in a beam. I should say it's a radical. Calcium fluoride has an unpaired electron spin. So if you just take a bottle of gas, you won't get any calcium fluoride. It'll react to make other things. So this free radical calcium fluoride beam is coming out of the mixing chamber here. And of course, there's other stuff as well. Particularly, I mentioned helium is flowing along in the beam as well. How can you slow calcium fluoride? By scattering light. It's an easy calculation to see that you need about 10 to the 4 photons, 10 to the 4 h bar k, to take out the forward momentum of the beam. So here's the electronic ground state of the molecule, labeled by X. It's a doublet sigma molecule, and we're interested in using the n equals 1 state, that is to say, the state with 1 unit of rotational angular momentum. And it also has vibrational levels. I just draw the first 2 here. Up here is the first electronically excited state, and you could imagine exciting that, but the problem with exciting that is that 3% of the time it will decay spontaneously down to the v equals 1 level, and 10 to the minus 3 of the time it will decay to v equals 2. So you would have to have a lot of repumping lasers to make this slowing work. And a simpler approach is to use the B state, which is the second electronically excited state. And so we drive that at 531 nanometers. And the nice thing about the B state is it has a rather small leak to v equals 1, 0.2%. And for this purpose, negligible leak to v equals 2. We don't have to worry about it because we're only going to scatter 10 to the 4 times. So we need a repumper because it will surely drop into v equals 1, and we need to push it back again. So 2 lasers are required to scatter 10 to the 4 photons from the beam. And here are their wavelengths and their powers. Irritatingly, the molecule has hyperfine structure. So there are 4 levels in each of these vibrational states. So one needs some sidebands on the light to make sure that we excite all the hyperfine levels. Otherwise, we just optically pump into one of them. So that's the scheme for slowing the beam, and it works really well. So here's a picture showing the initial velocity distribution in black. That's the velocity starting out, in this case, about 130 meters per second. The laser that is doing the decelerating along here is tuned to be resonant with molecules at this speed here, about 170 meters per second. And so those molecules get slowed down, and you see in this distribution here, that's the slowed velocity distribution. They're now traveling at 103 meters per second. Why don't they go any slower when the laser is pushing? Well, the answer is the Doppler shift. So the Doppler shift is now whatever corresponds to 75 meters per second. That's big enough that the molecules stop scattering the light. They're detuned from resonance by the Doppler shift. And the way to fix that is to start chirping the laser frequency. So here we've chirped it at 7 megahertz per millisecond, and now you can see that it's slower. And the more you chirp, the slower it gets. With the biggest chirp, we get molecules below 15 meters per second. And we like 15 meters per second because that is roughly the capture velocity of the MOT. So below 15 meters per second, we measure about 200,000 molecules per pulse of the beam. And they arrive in a cross-sectional area of about 1 square centimeter. That's slow enough to capture in a MOT. So the next part of the story is how does the MOT work? Here is the electronic ground state again. I introduced you to those two vibrational levels. Now I want to add some more. I'm still working with the rotational state n equals 1. And I'm going to excite to this A doublet pi a half state. This is the state that I didn't like to use for the slowing, but I'm going to use it for the MOT for reasons that I don't have time to go into. So we excite that at 600 nanometers, and then it has these decay branches. I want to mention here that this is rotationally closed. The reason that we start from n equals 1 is if you then excite to n equals 0, the only place the dipole selection rules will allow you to come back to is n equals 1. So you don't have to worry about repumping the rotational states. This was first noticed a long time ago. So it's rotationally closed, but it's not vibrationally closed. It has all of these leaks, and therefore we need lasers to repump the leaks. And here are the colors that we use. And again, each one has hyperfine structure. And before we get to the MOT, we have to slow the molecules down, as I showed you on the previous slide. So there are a lot of laser colors and lots of sidebands. There's a big table full of lasers. But with the advance of solid-state laser technology, it's not like the old days of dye lasers. You can actually run this many lasers, and they just work and work and work. So life is wonderful from this perspective. There it is. That's a MOT of calcium fluoride. It has 20,000 molecules in it. And the size of this particular cloud is a few millimeters. Once we have the MOT, of course, then we like to look at it, to poke it and see how it behaves. So one of the first things we did was to watch the atoms sloshing back and forth in the MOT to see if we could measure the spring constant for the conservative part of the trapping potential. And so here it is, plotted oscillation frequency as a function of the intensity of the laser. And what I want to show you is this. So the red dots are, of course, the experimental results. The blue line is a theory. It's simple Doppler theory, slightly modified to take into account the many levels that a molecule has that we are exciting with all these different laser colors. But it's basically just Doppler theory gives us correctly the conservative part of the interaction potential. Here we notice that the longer the molecules sit in the MOT, the more they go away. In fact, it's proportional to the scattering rate. So what we think is that at the level of about a part in a million, there is a leak out of the excited electronic states that we don't control, that we don't know about. and we have not yet understood what that leak is. But fortunately, with a loss rate of only a few per second, there's a lot we can still do. Another thing here that I show you here is if you optimize the trapping of the molecules into the MOT, you can then ramp up the magnetic field to see if the cloud will compress. And what we find is that it does compress. Now, people working with alkali atom MOTs know very well that there's a limit to how compressed you can make the MOT before it becomes optically thick. And then the rescattering of light just causes the size to stay constant. But here, the density is still low, and we find that we can ramp up the axial field gradient all the way up to whatever this is, 120 Gauss per centimeter or so. If we go any higher, we just fry the coils. So if we don't want to destroy the experiment, we have to stop. But what you see is interesting, that the density is just increasing linearly, and we don't know how far you can push that. Now, finally, the most important question is about the temperature. So in the usual way, we measure the temperature by watching a freely falling cloud expand, and we see how quickly the expansion occurs. This shows us that for low-intensity MOTs, the temperature goes down when you turn up the intensity. But it reaches a minimum, and if you continue to turn up the intensity, the temperature goes back up again. And that minimum is still quite hot in comparison with the Doppler theory. So although the conservative part of the trapping potential is well described by Doppler theory, the dissipative part is not, and that is why the temperature is high. So let's understand what's wrong with the dissipative part of the Doppler theory. It has to do with dark states. Let me just remind you that in order to make the transition be rotationally closed, we chose a rotational state 1 in the ground state and rotation 0 in the upper state. That means that you have 3 times more sublevels down below than you do up above. The number of sublevels is just 2n plus 1. So that guarantees that you have dark states, because you have many more ground states than you have excited states. What do the dark states do? Well, they have a light shift. The bright states have a light shift. They start shift downwards. The dark states don't see the light. Inside the MOT, the polarization is varying all over the place. So here's a picture of some light with polarization varying all over the place. This shows you that the optical stark shift of the bright states is going up and down, while the optical stark shift of the dark state is doing nothing because it's dark. It doesn't know the light is there. Now, if I have a molecule in the bright state, it will interact with the light, and that has the chance to optically pump it into a dark state. And now it may roll along in the dark state, but here is a region where the two are very close together, and it's easy for them to be mixed. So the molecule could jump into the bright state, and then it would roll down the hill and get faster. Here it would optically pump again. Then it would come to a place where they're mixed, and it would roll down the hill again. So the effect of this is that the molecules, if they're traveling slowly, the molecules will be heated by falling downhill. This is very familiar. It's Sisyphus heating, except for the sign of the effect. So when you make a rubidium MOT, it's unexpectedly cold because the Sisyphus cooling is stronger compared with the Doppler cooling. That's because the energy that you can take out is coming not from a scattering rate, but from the light shift, which can be very big. Here, it works exactly the other way round. And it's because, in this case, we have too many ground state sublevels, and therefore we have dark states. Fortunately, there is a nice way to rescue the situation, which is discussed first in this paper and later in this, which is just change the sign of the detuning. But if you shine red detuned light on a 2-level atom, it will push the ground state down. But if you shine blue detuned light, it will pull the ground state up. So all we have to do is move the light state up above the dark state, and then you get Sisyphus cooling. So the explanation, why is the MOT too hot? It's because with red detuning, Is that for me, Dan? 5 minutes? Okay. With red detuning, we have, for slow molecules, we have Sisyphus heating. But we now understand that we can fix that problem by switching to blue detuning. Let me just show you a very nice numerical model that was recently made by Jack Devlin and Mike Tarbut. It's not published yet, but it's an attempt to make a full three-dimensional model of everything that's going on in this system, including all the coherences and so on. And this is the curve that they see of essentially the force versus the velocity. With red detuning, you have here negative acceleration as Doppler cooling. But for these very low velocities, you have Sisyphus heating. That's what I've been telling you about. If they go fast, the molecules just skate over the tops of the wave, and they don't see this Sisyphus heating. They just get Doppler cooled. That's what this is showing you. But if they're going slowly, they'll be heated away from zero velocity by the effect. And when they switch to blue detuning, now you get Sisyphus cooling and Doppler heating. So the model says that our MOT should have a temperature of 6.5 millikelvin at 300 milliwatts per square centimeter, and it does. That's up here. It also says if we lower the intensity of the light, temperature will go down to half a millik, and it does. And finally, it says if we switch to blue detuning, we can lower the temperature to 30 microK instead of a millik. So here's the experiment. For subdoppler cooling, we switch to blue molasses. First, we load the MOT. Then we ramp down the intensity of the light to get it as cold as we can. Then we switch off the MOT magnetic field, jump to blue detuning, turn the intensity back up again to get strong cooling, wait a little while, and measure the temperature. And the first experiment that we did to do that shows this fabulous cooling here. So in 1 millisecond, the temperature has come crashing down to here below this dashed line. And that dashed line is the lowest temperature that it's possible to have with Doppler cooling. After a bit of fine-tuning, we get a temperature of 52 microK. Playing with the numerical model showed us that we can actually do much better than that. And so most recently, the model has told us that what we should have is, okay, here's the electronic ground state and the A state. We have these vibrational repump lasers. And a single frequency of far detuned blue cooling light should work really well. And it does. So that's given us a temperature now of 7 microkelvin. It's amazing. You need 100 megahertz detuning from this bottom level, which is 250 megahertz detuning from the top level. It's all about the dark states. So now we have a cold molecule cloud. The natural thing to do is to trap it and try to make some coherent manipulations. Here's the n equals 1 manifold. After cooling, these states are all occupied. If we turn off the laser that excites F equals 0 here, we can optically pump into this state. So there they are. All the molecules are now sitting in this one sublevel, F equals 0, MF equals 0. A microwave transition will drive them down to n equals 0, the rotational ground state. This level here is a stretched state. It has a magnetic moment of 1 Bohr magneton. So it's trapped. And in the trap, we get 5,000 molecules with a density of 2 million per cc. And there's another trapped state, this one up here, which is also a stretched state, so also a 1 Bohr magneton state. These are both trappable. When we put them in the trap, we see that the loss rate depends on the helium flow, because in the beam, as well as calcium fluoride, we have helium. And that's banging into the trapped molecules and kicking them out of the trap. So even though we turned the helium flow all the way down as far as we could, we still had some loss. And so we put in a shutter, and now the loss rate fell to 0.22 per second, which is in fact the expected loss rate from blackbody heating, just from microwaves in thermal equilibrium. We can Rabi flop these trapped molecules. Here's a picture of some Rabi flopping. And once you can Rabi flop, you can do Ramsey interference. So this is a Ramsey pattern made by molecules in a magnetic trap. And we had a pi/2 pulse, and then half a millisecond wait, and then another pi/2 pulse. So now you have a nice Ramsey pattern. It's easy to measure the phase coherence time, T2. 0. So we do that by just varying the time between the Ramsey pulses, and we get a T2 of about a millisecond, which is due to the fact that these two states, although their magnetic moment is approximately a Bohr magneton, they do in fact differ by 70 parts per million. So that's the current state of play for these sort of coherent manipulations in trapped molecules. I just want to mention in passing that subdoppler molasses cooling also works for YbF, which is the molecule that we like for measuring the EDM. This shows a YbF source and a beam with a probe laser, and in the camera we just see, oh. In the camera, we just see this streak of fluorescence. But when we turn on the red detuning, oh, it's died. There we go. When we turn on the red molasses, we see this very interesting structure here. With a second probe laser at a different distance, between these two, we can work out that the velocity of these bright peaks is about 1 meter per second. And what's happening is the Doppler cooling is pushing them in towards the middle. It's lowering the velocity, but the Sisyphus heating is pushing them back out. And they actually like to collect at a velocity of around about 1 meter per second. With the blue molasses, it works fabulously. So there's a very bright spot inside here. It gives us very strong Doppler cooling, and the transverse temperature is less than 100 micro-K. It's difficult for us to measure how cold it is. So where are we going? We're working on making an array of tweezer traps for calcium fluoride molecules. This is for quantum simulation kind of applications. This is an old idea of using molecules for quantum information processing. We've built a dual rubidium calcium fluoride MOT for studying ultracold collisions, and we have an experiment to measure the electric dipole moment of the electron with such a high precision that we will be probing new elementary particle physics up to 300 or 400 TeV, which is far beyond what any collider experiment can see. Finally, I want to say that the Center for Cold Matter is run by the three of us, Mike Tarbert, Ben Sauer, and myself. I especially want to highlight Mike Tarbert in the context of this because he is the one who has had important insights into how a MOT works for molecules and how laser cooling works for molecules. And finally, thanks to Luke, Hannah, Noah, Jung-Suk, Sharunas, Michael, Jonas, Tom, Moritz, James, Jack, and Stefan for doing the actual work in the lab. Thank you.